Ladies and gentlemen, good morning. My name is Ricotta and I'm from University of Padua. The paper that I will present to you is titled Estimating the Specific Heat Loss from Temperature Measurements in Metal Fatigue Theory and Experiments. Fatigue is an irreversible process accompanied by structural changes, localized plastic strains, and energy dissipation. The temperature increment of a metallic material undergoing a fatigue test is a manifestation of the thermal energy dissipation. In particular, during a fully reversed elastoplastic fatigue cycle, material temperature oscillates to the superposition of two different phenomena. The thermoelastic effect, that is a reversible phenomenon, combined with temperature change, are related to the plastic energy dissipated as heat twice in one cycle, here named as delta Tp. Barr and co-authors recently shown that concerning fully reversed tension compression fatigue test, delta Tp is spread out into several harmonics of the discrete Fourier transform of the temperature signal, starting from that modulated at a double frequency of the applied load, which however retains the most significant contribution. And then, some authors, as Akai, Palumbo and co-authors, investigated the discrete Fourier transform of the temperature signal during a fatigue test and evaluated the intrinsic plastic dissipation per unit volume of material per cycle, starting from the range of the second harmonic, here named as delta T2. In this paper, the correlation between the intrinsic dissipation and the second harmonic of the temperature signal has been investigated by means of the following general expression, where ρ is the material density, C is specific heat, beta is a coefficient to be determined, and the coefficient 2 takes into account that the intrinsic dissipation associated with plasticity is produced twice over one loading cycle. Under the hypothesis that dependence of the material state on temperature is small, because temperature variations are too small to induce phase transformations, the energy balance equation can be written in terms of power, as you can see here, where this term represents the plastic strain energy rate, this one the store energy rate responsible for fatigue damage, this one represents the heat rate per unit volume due to thermoelasticity, and the last one represents the heat generation rate per unit volume supplied to or extracted from the material by external sources. Let us define D1 as intrinsic dissipation, and assuming at the moment that the intrinsic dissipation and thermoelasticity are null, the first principle of thermodynamics written in terms of power can be written as follows, that can be recognized as the general heat conduction equation. Letting the Laplacian of temperature as Q dot and Q dot P as D1, you can see here that the first principle of thermodynamics can be written in this form, where Q dot P and Q dot thermoelastic can be thought of an equivalent plastic and the thermoelastic power heat sources in a purely thermal problem. If the power quantities appearing in the previous equation are added over one loading cycle, the equation simplifies in this form, because the contribution of the thermoelasticity vanishes because it consists of a reversible exchange between mechanical and thermal energy, which does not produce a net energy dissipation or absorption over one loading cycle. When during a fatigue test the temperature stabilizes because equilibrium is achieved between the heat production in the specimen and the heat transfer to the surroundings, T dot becomes null, and then the equation simplifies in this form. If the fatigue test is suddenly stopped at T equal to T star, Q dot P will become 0, and then Q dot can be measured by experimental measuring the gradient, the temperature gradient at T equal to T star, and then divided by the load test frequency, we can experimentally evaluate the heat energy dissipated by the material per unit volume of material and per cycle, according to this equation proposed by Meneghetti 2007. Assuming that the stabilized material temperature is a periodic function, it can be expressed in terms of its Fourier series, where the coefficients, the parameters Ts, Ak, and Bk can be expressed in terms of according to these equations. Therefore, the second harmonic of temperature signal can be calculated according to this expression, and its range can be evaluated according to this equation. Under the hypothesis that, first, the plastic strain energy rate is fully converted into specific energy rate, and second, that a uniform stress state and adiabatic condition exist, the first principle of thermodynamics can be written according to this equation, where Tp is material temperature due to plasticity and T thermoelastic is the material temperature related to thermoelasticity. And then, by the integration of this equation, we can evaluate the material temperature evolution over one loading cycle. Let us consider an elastic plastic material obeying to a Ramberg-Osgood load under fully reversed stress control fatigue tests, with the aim to analytically evaluate the plastic strain energy rate over one loading cycle. The coordinate reference system has been set at the lower tip of the hysteresis cycle. As a consequence, in the time domain, the stress range can be written according to this equation, and the elastic component of the strain according to this equation. The plastic component of the strain along the loading branch of hysteresis cycle can be written according to this equation, and finally the plastic strain evolution along the unloading branch of the hysteresis cycle can be written according to this equation. Plastic strain evolution, the plastic strain energy rate in one loading cycle has been calculated, and its trend is shown in this picture. Finally, by the integration of the plastic strain energy rate, the temperature variation due to plasticity has been calculated, and the result is shown in this equation. Temperature trend due to plasticity is shown in this picture. That was calculated according to this equation that I showed you before in the previous slide, and the temperature trend is compared to the plastic strain evolution over one loading cycle. Then the temperature trend related to the thermoelastic effect was calculated according to this well-known equation, and its graph is plotted here compared to the elastic strain evolution calculated over one loading cycle. Finally, the material temperature was calculated simply adding the thermoelastic effect and the temperature evolution due to plasticity. It's worth noting that we are assuming adiabatic conditions, and then at the end of one loading cycle the material temperature is increased with respect to the beginning of the facile cycle, as you can see here. In the actual laboratory test conditions, the average material temperature stabilizes after achieving the thermal equilibrium with surroundings. In other words, the self-heat generated in one loading cycle is exactly transferred to the surroundings in the same period of time. This experimental situation has been simulated in our work by considering an idealized, simplified and uniform heat sink R dot that can be expressed as the plastic energy averaged over one loading cycle multiplied by the test frequency, and then the material temperature can be expressed according to this equation. Finally, the material temperature as well as the applied sinusoidal load were expressed with respect to the classical reference system simply by shifting this expression. You can see here the green line represents the material temperature evaluated with respect to the classical reference systems. The red line that is here represents the plastic temperature obtained after cleaning the temperature by the thermoelastic effect that is here represented as the first harmonic of the temperature signal. And as you can see here in the detail of this picture, that the plastic temperature is not a sine wave as pointed out by Barr and co-authors. And then we can see also that the range of the plastic temperature is higher than the range of the second harmonic. Finally, the beta parameter was evaluated according to this equation. It was found that beta depends only on the cyclic harmonic coefficient n. The proposed analytical frame was applied to experimental tests that we have carried out recently for the rapid evaluation of the fatigue limit of AISI 304 low carbon stainless steel bar. In that paper, we have carried out step loads fatigue tests by imposing incremental stress amplitude ranging from 270 up to 405 megapascal. Two consecutive temperature acquisitions were performed using, in both cases, 10-second long sampling window with a frequency acquisition of 200 Hz. In particular, the first acquisition consisted of exactly 10 seconds of running tests, followed by the second one capturing the machine stopped at time t equal to t star to measure the cooling gradient and then to evaluate the Q parameter by using the classical approach proposed by Professor Meneghetti in 2007. On the contrary, from the first acquisition, the range of the second harmonic of the temperature signal delta T2 was evaluated by post-processing the mean temperature evaluated in a small area placed in the center of the net section of the specimen by using the MATLAB commentator software. And then, having the delta T2, we have evaluated the Q parameter by using the analytical approach proposed in this paper. During the fatigue tests, the hysteresis cycles were measured and the stabilized hysteresis cycles measured at each applied stress level are shown in this slide. Having the area of the hysteresis loops, the W applied stress amplitude trends were fitted by using this well-known equation, which assumes amazing material behavior. The results of fitting procedure was carried out considering only the data clearly below and above to the knee points, as suggested in our previous paper. it can be seen that different values of N and K were found for a single specimen because of the cyclic evolution of the tested material. During the step load fatigue tests, the material temperature was monitored by using an infrared camera to evaluate the Q parameter according to equation 1 proposed by Meneghetti 2007 and according to equation 5 that is proposed in this paper. In the figure, you can see the second harmonic of the temperature signal as well as the succeeding cooling gradient. It can be seen that the range of the second harmonic is of the order of hundredth of Celsius degree, while the temperature drop measured during the cooling gradient is 1 order of magnitude higher. Therefore, the influence of noise has a different way on the signal-to-noise ratio, being significantly more critical on the delta 2 evaluation. This slide shows the Q parameter evaluated according to equation 1 and according to equation 5 for each tested specimens. It can be seen that the data relevant to Q evaluated according to equation 5 are closer and closer to that calculated according to equation 1 at progressively higher applied stress amplitude, since the range of the second harmonics to the noise ratio becomes higher and higher. In the author's opinion, this is related to the fact that the range of the second harmonic is of the order of hundredth of degree and then comparable to the noise affecting temperature measurements. The problem of the evaluation of heat energy density dissipated by the material per cycle, the Q parameter, by means of the discrete Fourier transform of the material temperature was analyzed. An analytical model was developed based on the first principle of thermodynamics under the hypothesis that the rate of plastic strain energy is totally converted into the rate of specific heat energy, and the uniform stress rate and adiabatic conditions are guaranteed. The analytical model was applied to the case of an elastic plastic material. It was found that the range of the second harmonic is correlated to the Q parameter by means of a multiplicative parameter beta, which depends on the cyclic strain hardening exponent of the material. The Q values calculated according to the analytical model have been compared to those measured during the same tests by using the well-established experimental procedure proposed in the past by Meneghetti. It was found that the results obtained by following the two approaches are closer and closer between them for progressively higher applied stress amplitude. In the author's opinion, this is related to the fact that the range of the second harmonic is of the order of hundredth of degree and then comparable to the noise-affected temperature measurements, at least considering the material and the test condition analyzed in the present paper. Thank you very much for your attention.